Okay, we are now ready to talk about FM synthesis, which is going to be the star of the show when it comes to creating cheap digital musical instruments. Now, there's actually kind of a rich, interesting history behind this. So this was something that was discovered in the late 60s, early 70s by this professor at Stanford. Just a guy messing around with audio who discovered this completely by accident. And it ended up being an extremely lucrative idea to the point where it actually funded this lab at Stanford for years to come. So what happened was this thing was invented around then. Then some Japanese company approached this guy, John Chowning, the professor, and they eventually made this synthesizer called the Yamaha DX7, which was the first commercially successful digital synth that was based on FM synthesis. And I mean, man, popular music in the 80s used this all over the place. You can see, it sold 200,000 units. So definitely, they were making a lot of money off the patent proceeds here. But just to give you an idea, this is the sort of thing we're going for here. So you might recognize this tune. So really what you hear, the bass at the beginning. They have a number of instruments here, but the bass. So we're going to learn to make that sound using FM synthesis. Okay. So it's a really cool idea, discovered completely by accident, and just completely revolutionized music making in the 80s. And because it was so cheap, it actually only requires 2 sinusoids. It was also used in a lot of video game music in the late 80s, early 90s. Now hardware's, not so expensive to do the same kind of thing, but it actually has a unique timbre, so people still use it. Okay, and what's interesting is you can actually synthesize all sorts of different instruments under the same framework. And that's what made it so powerful. You only had to use 2 sinusoids to make everything from pluck strings to bells to brass to drums, even to voice. And so this made it extremely attractive for cheap hardware to do these good approximations of real world things. All right. So let's go through John Chowning's journey and figure out how he came up with this. So it all starts with something we've already seen, which is vibrato. I should actually give a demo of vibrato myself. So let me do that. So this is a violin. A little bit out of tune actually at the moment. Hadn't picked it up for a while. But, okay, so here's an A, concert A. Pretty stable right there. But if I move my finger back and forth, what I do is I actually this amount of string that I'm bowing changes its length ever so slightly, so that the frequency actually goes back and forth, and so you hear this interesting color that's very commonly used for artistic means. So let's do that in code again, which we've already done, but just to remind us how this works. So what we have is this general form of some waveform, which is cosine of 2 pi, and then on the inside is a function of time. And so, we saw that the general sinusoid fit into this framework. I could write, as an example, so remembering actually that what I hear is the instantaneous frequency. So we hear actually the frequency f prime of t. So at a particular time t, the frequency we hear is actually the derivative of this function at time t. So as an example, let's specify the derivative. Let's say the thing that we hear is always a constant frequency. So I'll call that just f naught. So in that case, the antiderivative is going to be just f naught times t plus c, but that's just a phase change. We're not going to worry about that for the moment. And so the function that we get is our good old sinusoid, which is cosine of 2 pi, and then I'll plug this in. So f of t turned out to be f naught t And you know what? I will do the plus C, right? So really, if I'm being pedantic with the antiderivative, there's a plus C there, and that's my phase. Okay, so some arbitrary phase. So look, I just re-derived the formula for a sinusoid from this more general formula where I can put any function in here that I want, recognizing that the frequency that we hear is the derivative. But what if we want to model vibrato? So in that case, we actually, so for vibrato, we actually want to have a frequency that deviates. So I want to introduce some terminology now that I didn't use last time, but I want to match John Chowning's paper. So I'm going to use the same terminology that he used. And I highly recommend looking at this paper, actually. The first few pages you should be able to follow, more or less. And, you know, the further along we get in the course, the more this you'll be able to understand. But anyway, let me use his terms for now. So what I'm going to have is a couple different things. One of them is called the carrier frequency. This is the center frequency, or carrier frequency of vibrato. And you may, at this point, you may be asking yourself, what does vibrato have to do with a trumpet sound or drums? Okay, we'll get there, but just bear with me for a moment. Okay. So it's called the center frequency carrier frequency. So in this case, that was the concert A for me, right? Okay, so we have another frequency called the modulation frequency. And this is the frequency. This is how quickly you're going back and forth around the center frequency. Okay. And then we have a third parameter called D, which is the modulation deviation. So this is the maximum amount that the frequency changes, that the carrier frequency changes as modulated by FM in either the positive or negative direction. Okay. So now I have enough information to define the derivative. So the derivative is the frequency I hear, so that frequency should be the carrier frequency plus the maximum deviation times the cosine of 2 pi frequency modulation times time. Okay, so here is the equation that describes all these things. So I have my center frequency, or my carrier frequency. I have my modulation frequency. I have how much the modulation frequency is causing me to deviate. And here's the equation. So usually I'm at the center frequency, but I'm going to oscillate around that with a magnitude of D, or an amplitude of D, at a rate of this many hertz. So we know enough to take the antiderivative of this. We've all had Math 111. So let me just do it. So if I integrate this, I get FC times T plus, okay, I'm going to use the chain rule here, so it's going to be D over 2 pi times the frequency modulation, the modulation frequency, times the sine, right, the antiderivative of cosine is sine, 2 pi FMT. Okay, so here is our thing that we can now feed into our cosine. So our final waveform is going to be cosine of 2 pi times all this stuff. If I distribute it through, it actually cancels the 2 pi down here, and I end up with this expression. Oops, let me close my parentheses here. All right, so here is the expression for the waveform that we have for creating vibrato. So let's just test it out real quick. Let's say that, just as an example, I'll make I'm going to stick with concert A. Let me just try to do what I did on the violin a moment ago. So I'll say that, well, first of all, let me set up my audio sample. So I'll say sample rate is 44,100. The time is equal to NP to A range. Sorry, maybe we'll do 3 seconds of audio. Okay, now let me say that the modulation or the carrier frequency is concert A. Modulation frequency, what was I doing? Maybe about 8 vibrations per second, maybe 5, I'm not sure. We'll listen to it. And the deviation, let me make it maybe 10 hertz. Okay, so going from 430 hertz up to 450 hertz around my center of 440. So my waveform is going to be cosine of 2 pi carrier frequency times t plus d over fm times beta sine 2 pi fm t. All right, so let's listen to this. I spelled A range wrong. What about now? Okay. I think I was going a little faster than that. Let me make it just 2 seconds of audio. Let me dial it up to 10. Okay, maybe that's a little fast. Yeah, that's about what I was doing. Okay, so I guess I was going about 7 times a second, back and forth. All right, cool. So we got it. Are we done? So here's the really interesting thing, and this is what John Chowning started to play with. So this is all well and good. This is, I can do vibrato this way. But if you take this framework and you really push it to its limit, some interesting things start to happen. So how can we push this to its limit? Okay, well, a couple ways. So one of the things I can do is really dial up the deviation. So here it was only 10 hertz, but what if I make it 100? Let's just listen. All right, so that sounds kind of interesting. Let me just show you what this looks like in the waveform. So let's just look at maybe the first 100 milliseconds. Okay, even there we can't quite see it. Let me see. Let me go to half a second. No, that's too much. Okay, so you can kind of see the pattern here that it goes high frequency, then a little lower, then high, then low. Yeah, so high, a little bit lower, higher, a little bit lower. I make this even more extreme. Maybe I make it 200. Now you can really see the difference. Really bouncing. I'm not going to be able to do that on my violin without breaking the thing, maybe. Or breaking my hand in the process. And what if I made the deviation as much as the carrier frequency? So what you'll see is this thing actually comes to a stop. It goes all the way to frequency of 0. Okay, so we're already starting to get some pretty weird sounds. But we're not really sounding like instruments yet. So there's another parameter we can tune here, which is the frequency of modulation. Let me start to push this to its limit as well. So that was 7. Actually, just so you can hear the effect of this, let me move the deviation back down to 10. Okay, so let me make this frequency of modulation 20 now. Okay, that's pretty fast, right? You can hear that it's deviating, but it's going faster than I would probably normally go. Let's dial it up even more. Now we're starting to hear something interesting in terms of the timbre. So we're hearing more than one note here. And as I move this up, I mean, this is starting to oscillate really fast in terms of the change around the carrier frequency. Hear another note. And actually, often, people will move it all the way up to the carrier frequency. That sounds kind of like a pure tone, but here's the interesting thing. If I make the deviation large as well, so if I make the deviation also on the order of the carrier frequency, now I'm getting something that's sounding a little bit like some of the stuff we did a moment ago. This is a much richer sound. So if I dial up both the modulation frequency and the deviation, I start to get some interesting things. Now, I do want to rewrite this equation real quick in a form that Chowning used in his paper, because it'll make it easier to express how we're tuning some of these ratios. So this ratio, actually, the ratio of the deviation to the modulation frequency, not to the carrier frequency, actually, to the modulation frequency. He calls that the, let's see, what does he call it? The modulation index, I believe. Yep, the modulation index. Okay, so that's a deviation over the modulation frequency. So the modulation index, I, is defined as the ratio of the deviation to the frequency of modulation. So I can just replace this whole thing with an I. And actually that makes the equation a little simpler. It's, I can see it's just cosine of the carrier frequency plus that I times the sine of the modulation frequency. Okay. I also want to think about the ratio of the modulation frequency to the carrier frequency. I don't want to talk about that now. I'll defer that to the very next video, but that's another ratio that we think about. But let me I want to explore the effect of this ratio for a moment, and then I'll have you do a little exercise. So let me go back and I'll do a similar example, but I'm going to, instead of defining D, I'm going to define this I. So I'll start with I of 1. And yeah, let me actually make the carrier frequency and the modulation frequency the same for a moment. And I don't need to plot this anymore. It's going to be kind of hard to see anyway. Okay, so that's what we get when the ratio of the peak deviation to the modulation frequency is 1. What if we really dial up the peak deviation? So suddenly we're 2 times the peak deviation. This is going to be kind of weird in the signal because it's going to go into a negative frequency. It's going to do something called a phase reversal. But anyway, so what does this sound like? Okay, let's go back. So this gets a little brighter and a little grittier. What if I move it up to 3? Even more so, actually. Okay, so one really interesting thing already. So not only did we make these weird alien sounds in this framework, right? If we really made that frequency modulation huge but at a low frequency. But when we really dial everything up, when we start to mess with just this one parameter, we get a whole bunch of different sounds. So this is going to be the basis for how we design our instrument sounds. Okay, but let's just quick do an exercise to make sure that we have internalized this formula. And then we'll start to examine more examples.